Good morning, everybody. Welcome back. Into day 4 now, the last day. Finally, we made it. Does anyone have any questions, anything on their mind from yesterday, or any tutorials that they tried to go through last night that they've having trouble with? No, that's fine. If you do have any questions throughout, once again, unmute yourself or chuck it in the chat. Now, today we're going to cover a few things. We are going to start with some nitty gritty again, just get the boring stuff out of the way. Ahmad, we will be sharing the recording. I believe Hashan should have that. I'll let him know in the break to put it up. But they will all be going up, so there's no need to worry about it. So we're going to start with a little bit of the more in-depth stuff. We're going to go into some solver settings, some stuff that we covered yesterday, but I'd like to go through it again with the slides because I feel like the slides give a bit more context than just looking at the GUI. The GUI is the graphical user interface of Fluent. And then once we do that, we're going to go into some heat transfer. Then we're going to look at a case that I've set up for heat transfer. Go through the settings for that, talk a little bit about that case specifically and how that was used for a digital twin. And then we're going to look at some multi-phase stuff and then some adjoint, and that'll probably do us for the day. So we'll see how long that takes us. But let's get started on the solver settings. So in our Fluent window, this is a case we'll be going through a bit later on. When we're talking about solver settings, we're talking about most of the things in this ribbon here. So these kind of coupling, pressure velocity coupling, spatial discretization methods, transient formulation, and into these controls, which once again, we did speak about yesterday, but we only looked at it on here. But I'd like to go through some of it on the slides before we move on. Okay, so back to the setting up physics tab at the start there, the solver, these major settings, these more general settings, we're looking at whether or not we're doing steady or transient cases. We know all about that. There's also the difference in pressure-based or density-based. It used to be that anytime you had a supersonic flow, you'd be looking at the density-based solver, but now pressure-based is good up to Mach 3. And it is the default and should be used for most problems. Now, this is the coupling, and a bit more context, that's this one here. So the pressure velocity coupling, simple or coupled, segregated or coupled. Oh no, so this is still talking about pressure and density. It looks very similar to the simple coupled, but we'll get to that in a minute. So the pressure-based solver, we're solving mass and momentum, then energy, and then species, then moving into the turbulence equations. And if we remember from our RANS equations from yesterday, mass and momentum is our U, V, and W, so our velocities and our pressures. And then we solve energy, and then we solve species. In the density-based, we've obviously got a varying density, otherwise we couldn't solve for density. And when we have a varying density, rather than using a constant density, which we do for most cases up to Mach 0.3, we then have our density varying as a function of pressure and temperature through our real gas equation. So you can see that instead of solving separately energy and species, so temperature and then the species, we can solve all of that in one go and then move into our turbulence equations. Remember, our turbulence equations for most of our applications will be the two equation set, K and omega or K and epsilon. This covered a bit yesterday, making sure that the size of our domain is applicable, is such that we're not going to get inaccuracies due to not resolving enough of the domain. So making sure that once we've solved our model, checking that as much as we can, our flow has gone back to a free stream condition before reaching the outlet. Into our solution methods. So we are looking at the difference between our segregated or our coupled. So up in here, our solution methods. In our segregated solver, we're solving UV, W, momentum, and continuity separately, and then moving into energy, whereas in coupled, we're solving them all at once. And why that's important is because the coupled method can be a lot more robust. But for certain applications, it may be unstable. You may have to solve in a segregated fashion, segregated being simple. But generally, you'll find behavior much like this, where you can see that we've gone for 2,250 iterations and we're still not quite converged, or we have converged. But in this case, we're converged by within 120 for the same case. Okay, so because we're coupling them together, each iteration takes a little bit more RAM, but it's a more robust and faster, generally converging solution. The difference of 3.5 hours to 13 minutes in this case. We did touch on a little bit on spatial discretization yesterday. So spatial discretization is important for all problems, really. And what it is when we're looking at our gradients, we're either looking at one cell to the left and right, or a couple of cells to the left and right. In the upwind scheme, we're looking at all the cells behind, so 2 cells behind. So each of these is just a cell in our grid. This is some velocity. This is some velocity in the cell next door, some velocity in the cell next door. For a first order upwind scheme, we're looking at the cell behind and getting our gradient based on that. For a more accurate understanding of our gradients, we can include more cells. So second order upwind scheme. Okay, and that's just going to give us a higher accuracy, but increase our computational cost. So you can see here that for a first order upwind scheme and a second order upwind scheme, there's quite a drastic difference in the actual output of a solution. This is a lot better and a lot more well refined. And that's just in here. So we can have spatial discretization for just gradients, for our pressure, momentum, and turbulent quantities. Turbulent quantities are usually okay, first order upwind, but you generally want to have second order for everything else where possible, and that is usually the default. Another application where higher order spatial discretizations is important is in the turbulence. I'll have to find that slide real quick. So if we remember yesterday in our different turbulence modeling approaches, we've got our direct numerical simulation and our large eddy simulation and our RANS models, so our K and omega. Sorry, I was just going through and muting people, so I couldn't hear it in the background. Now, to do a direct numerical simulation, as discussed yesterday, we need to have a really low mesh sizing so we can capture these turbulent structures, and a really high capturing these turbulent structures and a really high number of mesh elements. But on top of that, also, we'd like to have a fourth or a fifth order spatial discretization scheme in order to do that. Now, Fluent goes up to third order spatial discretization. So having a higher order spatial discretization can give higher accuracy and will allow us to capture more of the transient flow effects that would be experienced in a fully turbulent direct numerical simulation. It's another case where major difference between first order and second order. So you can see same boundary conditions, same grid, different discretization, different results. Into the next tab, we've got our controls. We did go through this yesterday, our under relaxation factors. So we've got an under relaxation factor for all of our equations. And remember that our relaxation factor is to do with the difference between the solution variable calculated at the two different iterations. So we've got our old, so at iteration, say 1, we've got this value for pressure, density, velocity. We then run our iteration and we get our iteration 2, we get another value for that pressure. Let's just call it pressure. So we got pressure 1 and pressure 2. When we use under relaxation, we don't take pressure 2 and then plug that into our next iteration. We take some fraction of pressure of P2. And the reason for that is because it allows us to converge more slowly to a solution. So with iterative numerics like this, you can often get the solution jumping around and not kind of numerical instability. What solution controls can do is by edging us more towards that solution, we can get more stable numeric performance. So we can see in here, I can hear myself. Someone's come in unmuted again. Okay, so we can see in here, we've got 2 different cases where we've used a really high under relaxation, so not very under relaxed at all, and a really low under relaxation factor. So we've really relaxed those values. So we're only stepping very gradually to the next iteration. You can see here, this one's taken 225 iterations to converge, but it's been much more stable. This one's a little bit less stable, but it's only taken 50 iterations to converge because we're getting there faster. Okay, and remember, we're assessing our convergence not only through our residuals, but through our output quantity of interest. So when using the coupled solver, you have the option of solving your flow in a pseudo-transient fashion. So we discussed that yesterday. Pseudo-transient is an under relaxation method, is a form of implicit under relaxation in terms of kind of a pseudo-transient, so a time step. We're introducing the concept of a time step into a steady state solution. We can either use the length scale method or a time scale factor. Works in probably much the same way as the under relaxation methods for pressure, velocity, etc. But this is kind of working in the temporal sense rather than the pressure sense or the velocity sense. So it's aiming to kind of under relax and make a solution a little bit more stable. Moving into reports. Now remember, yesterday we used reports to assess convergence. Because our residuals aren't the full picture. The residuals are just one part of the story. And remember, highly nonlinear, highly transient. Fluid flow is always highly nonlinear, highly transient, even for simple cases. Sometimes it can be really easy to get our residuals down. Sometimes it's not as easy, and we need to use things like our monitor points to make sure that our solution is converged. And we really want to see them just reach constant values. So if the output quantity of interest has reached a flat line and we can't, and our residuals are sitting up here, we might consider our solution to be converged enough for the use that we want. Monitoring convergence using residual history. Generally, a decrease in residuals by 3 orders, 1 to the -3 of magnitude, can be a sign of convergence. Scaled energy residuals should decrease by around 10 to 6. Scaled species residual may need to decrease around 10 to the -5. They are just guidelines for you to go on. The best practice is to also monitor quantitative variables like lift, drag, pressures, pressure drops, etc., and ensure that overall mass, heat, species conservation is satisfied. That's another really good one that I often forget to do. When we're running our solution, when we've solved, just always good to just double check that mass or heat is conserved by looking at mass in versus mass out at the inlet and outlet, or looking at heat in versus heat out at all of the surfaces where there is heat transfer. Our initialization schemes, remember yesterday we went through this, our initial guess, our first guess for what the solution quantity is in the cells is different for the different types of initializations. Standard is the fastest, but it'll just put a single value in all the cells that you can select. So standard initialization, all cells have the same value. Hybrid initialization runs through 10 iterations and slightly more realistic first guess. So it's a better starting point than standard, but takes a little bit longer. And then FMG, multi-grid initialization, is a much more realistic, non-uniform initial guess, however, takes longer to generate. So what that one does is it cuts the grid down, it bunches cells together and cuts the grid size down and runs through iterations on what is effectively a coarser mesh. And then you get this starting point that's a lot closer to the final solution. And really that just means that you're more likely to get to the solution A, and you're going to get to the solution faster B. Okay, that's really what I wanted to cover again in solver settings. Hopefully we can keep rehashing those as we look through the next few models that we're going to go through. We're going to have a brief look at heat transfer before we go through a model that we've built. Heat transfer is a really important CFD application, and CFD is really great for understanding heat transfer because it is you're able to directly model things like convection, and also radiation, whereas in other heat transfer applications like FEA, you have to make assumptions about what the convection coefficients are, etc. So when we're heat transfer modeling in fluid, all modes of heat transfer can be considered: conduction, convection, and radiation. Numerous processes can be included as appropriate. Fluid solid heat conjugate heat transfers are really good. And to model heat transfer, activate the energy equation. So all we're doing is ticking that box, and the energy equation, so that our Rand's equation with E, or with our enthalpy, is now turned on. And you have to apply, obviously, all of your temperature or your heat energy related boundary conditions. So this is our Rand's equation for energy. Remember, we've got our unsteady term, transient. Our convection must equal our diffusion terms, diffusive terms, and our source term. So conduction heat transfer. Conduction heat transfer is governed by Fourier's law and is usually just a function of the thermal conductivity of the material. So if you're using materials out of the database, it'll have some thermal conductivity in there already, but you can specify your own, and you can also specify them as kind of piecewise linear, piecewise polynomial, orthotropic. So we can have variable thermal conductivities varying with spatially with the axis of direction, and also varying with temperature and other factors. Convection heat transfer. This is our convection heat transfer equation. In Fluent, we're modeling this directly though. This is usually how you would specify this in an FEA model. You'd specify your heat transfer coefficient, and then it would calculate it based on the difference between the temperatures, the temperature in the fluid and the temperature of the surface. But in Fluent, we're actually modeling the conduction of heat into the air from the body, and as the air then can take it away. As a fluid moves, it carries heat with it called convection. Thus, heat transfer is coupled to the fluid flow solution. That's why CFD is really good for heat transfer applications. In natural convection, that occurs when there's a fluid density difference. So when density is temperature dependent, so we no longer have a constant density, we're turning on either a Boussinesq model or a ideal gas law. And when we heat up a gas, the density usually drops, and the difference between the density of the hot gas and the surrounding air will push that air up. Okay, so that natural convection is usually, it's a highly nonlinear phenomenon, and so good to be solved for with the actual fluid flow field. So of course, when we have this, we have to turn on gravity, because it's gravity that's going to drive that difference, drive that force, that pressure differential that forces the gas upwards with a differential temperature and a differential density. It's important to understand when natural convection has to be considered, because in our applications, when we're running the fluid flow simulation, we might not necessarily think we have to turn gravity on. We don't have to turn gravity on for all applications. When we're just doing a fluid flow, when it's forced convection and there's a high velocity of fluid, the majority of the energy transfer is due to forced convection rather than free convection. When we have a dominance, or at least, a kind of free convection is going to have a large enough effect, we need to make sure we're turning gravity on. And we can do that. We can assess that by looking at this Richardson number. Okay, so Richardson equals to 1, both effects must be considered. Far less than 1, free convection effects may be neglected, and greater than 1, forced convection effects may be neglected. So user inputs for natural convection. Define gravity in the operating conditions panel. Choose a temperature-dependent density model in the materials pane. If using Boussinesq, set the operating temperature. Operating density is ignored. So Boussinesq, what that is, that's an important model for modeling free convection. What it does is it allows us to have a varying density without having to solve for the full ideal gas equation. So PV equals MRT. That's your gas law, where your PV equals MRT, so M over V, so P equals rho RT. So your density is a function of pressure, the gas constant, and temperature. Instead of solving that whole equation to get that understanding of density, we just have this Boussinesq model, which just relates temperature to density. And we have our specified operating density, and then that will give us buoyancy effects with a more simplified model. So when we're setting up our boundary conditions, we can have any of these options at the walls. So these walls might be external walls, or they might be internal walls. External walls, we might be able to provide what we would do in an FEA equation, an FEA simulation, where instead of modeling directly the fluid flow on the external boundaries, we have some value for convection. So if we put convection, then we need to enter what the heat transfer coefficient is and what the free stream temperature is outside of our domain. Okay, so when we're talking about those walls, they're the walls, the external of our domain. We can also have radiation in there, and mixed convection and radiation. Radiative heat transfer is a mode of energy transfer where the energy is transported via electromagnetic waves. So we can have radiation in there as well. There's a bunch of different models that we can use for radiation. It's getting a little bit more higher level in terms of your CFD use, because it does become a lot more complicated. The actual equation for radiation, as most of us have learned, is basically just the Stefan-Boltzmann constant times the emissivity of the on the surface. So whether or not it's a black body or a white body or something in between, and it's a function of the temperature differential to the fore. So radiation is generally not a big effect. As you can see, the Stefan-Boltzmann constant is quite small, but it does become really big effect when your temperature difference is really high. So in most of your applications where you've got a temperature difference of, say, up to 100 Kelvin, don't use this as a law, but I'm just giving you an example. we may be able to ignore radiative effects. Once your temperature differential becomes really high, you're doing combustion applications where you've got the gas is 1200 Kelvin and your walls, external walls are 400 Kelvin, then you may need to have the radiative effects modeled. I won't go into radiation too much because it does get a bit higher level for what we need it for right now. But you can see here that in choosing a radiation model, there is 1, 2, 3, 4, 5, 6, 7 different models to choose from, all with varying degrees of fidelity and varying degrees of computational expense. So your Monte Carlo, the most accurate model, but the most computationally expensive. Also, you would have to have a really good understanding of the actual physics going on in the process, because you'll need to have all of the, say, the emissivities, the radiation parameters specified in the model. And our lowest fidelity is a surface-to-surface model. When optical thickness equals 0, S2S has comparable accuracy with discrete ordinates, and Monte Carlo at less computational expense. So when we're getting to things with optical thicknesses where there's nonlinearity in terms of what's being actually radiated from certain surfaces, then this surface-to-surface model is applicable. Go through these tutorials once again. Cannot stress enough how valuable these tutorials are. This learn.lepost website is. I really wish I had it when I was at uni. I didn't realize it was available. But the amount of information in there and the amount of skill increase that you can have by just going through that website is quite high. Okay, let me just check for questions. So the question, I don't understand how pressure-based solver can work for flows up to Mach 3. The flow chart of solver equations you just showed implies otherwise. Oh, I'm not sure what flow chart we're talking about, but the pressure-based solver does work up to Mach 3. The pressure-based solver does still include density. It's just based on pressure. So the density-based solver is solving based on density, but they can both include compressibility effects due to a changing density. Okay, so this one here is a Raspberry Pi and a 3D printed case. So this is a heat transfer model that we set up like last year, maybe early last year, the year before. And this was used in a really interesting application, actually. We used it to build a digital twin. So for those of you who are interested in digital twins, I think you should definitely check this out. I'll bring the website up. If I can find it real quick. So have a look at this to get a bit of a better context on A, what digital twins are, and B, how we built this model. So you can see here, I'll try and get a good image of the Pi itself. There we go, you can see. So for those of you who don't know, Raspberry Pi is just a little computer. It's actually underneath what we're looking at now. What we're looking at now is the Sense hat. We 3D printed a plastic case for it all to go in, and we put a little fan on there for the fan to be controllable. Now, the whole purpose of a digital twin is exactly how it sounds. You're supposed to have a digital representation of a physical component, and we use 3D simulation to tell us more about that component than sensors alone can. Okay, so in this case, we've got our Raspberry Pi, and we've got this sensor here for temperature, and we've also got a sensor in the CPU itself that tells us how hot the CPU is running. So what we did from there is we decided, okay, let's build a fluent conjugate heat transfer model. And what we can do with that is to get a good understanding of what the temperatures and in both of those locations, the sensor locations can be under different conditions, and we can match that up with reality, and then we can create what's called a reduced order model. But like I said, go through the video if you're interested. For those of you who are going into doing projects, do recommend doing something on digital twins. It's the future of industrial technology, and it's going to be providing a lot of value for clients. Question: could you show how to initialize a simulation with the results of another simulation performed on a coarser mesh? So that's the FMG simulation will do something similar to that. And that's done in here. And this is something I haven't shown you guys yet, but I think it's really important for you to understand. This is the TUI, or the text user interface. And we're just going back a little bit to talk about initialization. So remember, we need to have a good initial guess of our simulation. In order to use FMG initialization, you can see here we have to use the TUI, but you can see if I press enter in the TUI, you get all these options. So these are all different menus. I know that FMG initialization is in solve. So I go solve, hit enter again. You can see all of the options in here, and then initialize. Enter again, FMG initialization. It'll ask me, oh, because it's transient, I can't do that. But that's effectively how you do the multi-grid initialization. Q goes back levels, by the way. So in order to navigate this menu, so Q will go back. FMG gives you solves it on what's effectively a coarser grid and gives you a good initial guess. Another way to do that would be to file, export solution data. So you'd export solution data for pressure, velocity, pressure and velocity in all the cells, and temperature, and then you could basically patch that in. So by going into here, patch. So you can patch these values in to the domain to initialize with some pre-calculated values. Okay, so back to the case. So what did we want to do? We wanted to set up a model where there is heat generated at the CPU. And let's try and show that. So you can see this is our Raspberry Pi with our Sense hat on top. In here's our CPU, and then it had a little aluminium heat sink on top. What we want to do is we need to have the heat coming in through the CPU, because that's where all the heat's being generated when we run our Raspberry Pi. So what we did is we built the CAD model of the case with the Raspberry Pi inside, and obviously we generated our mesh, and our domain looks like this. Okay, so we've got all of our solid components and our fluid domain, and you can see that these outlets extend away from the actual the fluid domain on the inside. The reason we do that is because when we have a reversed flow, we have to have some specification for the backflow temperature. We don't want that backflow temperature to affect the solution too much, because really we want to solve what's going in. And in reality, that backflow temperature isn't not coming in at exactly ambient if it's right there, because the whole domain has kind of heated up slightly. So we move that away from the body, and that's why our domain looks the way that it does. These walls here are, what's the name of these walls so I can, slippy. There we go. So these are free slip walls, so they actually don't have any effect on the flow as well, because obviously we don't want them to act like walls, because that's not actually the shape of the domain. So they're just free slip boundaries. So we specify the shear to be 0, and the air can go along those with no friction force. Okay, so let's have a look at our mesh. We'll go through everything in order. So 1.5 million cells, not too big, and our quality 0.099. So that's not the highest quality. Remember, we're chasing 0.15, but if we can get above 0.1, that's acceptable. So this is just around 0.1, so it is acceptable. Go back through the lectures on day 2 if you want to refresh what minimal orthogonal quality actually is. Okay, so a mesh. Now in this zones, we've got a bunch of cell zones. So obviously each solid body has its own cell zone, so we can specify what the actual material is in those locations. So you can see in the CPU, we've got some chip material, and in that we've also got our source term. So this source term is some input quantity. We've called it power in this case. So if I open up my expressions, power's in here. And that's just specified as some watts per meters cubed. So some power per unit volume. So that's the heat coming into our system. And you can see, okay, so let's open another one. PCBs, so material name PCB. So I've spelled because it has a orthotropic material properties. And that is, it is much more conductive in the in plane as it is than it is the through plane. So if we go thermal conductivity of one of these solid PCB, you can see we've got orthotropic thermal conductivity. That's to get a more accurate understanding of where the heat's going in the system, because we know that conductivity of a PCB, of a printed circuit board, is going to be really high in the in plane and low in the through plane. So all of our different materials are specified. We've got 4 different materials in the system, and our fluid is just air. In our inlet, we either had a gauge total pressure, or it was also specified at some times as a velocity inlet. So when we do a 0 pressure inlet, that works much in the same way as a pressure outlet. And the reason we do that is because I wanted to understand what the heat transfer in the system was when the fan was off. So obviously when the fan's off, it's going to be highly free convection dominant. So we just had our gravity turned on and our specified operating temperature. And then when our CPU would heat up, the fluid flow would flow away. So the inlet at the moment is 0, but we could have that inlet as a velocity and matching the fan. Our outlets are 0 pressure outlets, and our walls are all 0 slip except for these external walls. Another important point about these fluid simulation, we'll go back. Remember, we can specify the external walls to have some convection or radiation. In this case, radiation is not going to be applicable because we're looking at temperatures between maybe 80 degrees Celsius and 20 degrees Celsius. But case external, that's these ones. So we can see we have a thermal boundary condition on the external walls to make up for, or to show, to allow for, sorry, take to account the free convection that's going to be happening on the outer walls due to, you know, the change in temperature. So it's a very low heat transfer coefficient. Free convection's generally between 5 and 10. And our free stream temperature will be the ambient temperature of the domain. So that's all of our boundary conditions. This one, I think we got a solution in here for a free convection. Yes, we do. And we can see the free convection in action. So you can see that there's not really any high velocity flow coming in at the inlets or the outlets. It's mostly the flow is being driven here by, these are actually colored by temperature. You can see the flow is actually being driven by the difference in temperature here. So we've got a high temperature here at the CPU, and the flow is just kind of going up and around the sense hat, that's printed circuit board, and out to the outlet. Okay, so remember the important thing we were trying to understand in this simulation was what is the temperature due to the energy into the system at the CPU and at the sensor here, so that we could match that up with the real values on the digital twin. Just have another look at some more plots. So it's just a temperature plot. Okay, so what we did with this is we then took that information and created a reduced order model. So I'll just show you briefly what we did. Might be good to show it in the video. So what we did is we simulated a bunch of different conditions. We had two different heat conditions. We had a low power setting and a high power setting. And you can see here that we had a constant fan, but we went from low power to high power, back to low power. And we run these in a transient sense because what we wanted to do is we wanted to get understand the step change between low power, high power setting, and also how the model reacted temperature wise through it with a varying fan. So we can see here, this was a low fan setting. So this is free convection. That's why things take a lot longer to get to steady state, but this is low temperature, then high temperature. And what we took all of these different conditions out and we used them as learning conditions for a reduced order model. So that's in here. So this is using Twin Builder's dynamic ROM builder. So if anyone's interested in this stuff, shoot me an email. There's a couple of people doing projects on digital twins at some of the unis, and I'd recommend doing it yourselves if you're interested. So once we got that data out, we could then create this reduced order model. That's what the reduced order model looks like here. And this is Twin Builder. This is our system simulator. And we can have this fan and power information coming in from the live model. Okay, so this links out to what's called an IoT platform. That IoT platform links out to the Raspberry Pi in real time, telling us what the fan power currently is and the power setting currently is. So how much heat's coming into the system and how hard the fan's blowing. And we enter that into our reduced order model, which is a reduced order model of our fluent model. And that'll tell us what the sensor temperature and the CPU temperature should be in real time. And that comes back around into our IoT platform for us to display and compare to the actual model. That's our IoT platform. You can see that we've got our different things. These all link out to either temperatures, to either sensor data, or to other bits of code, or to our digital, our Twin Builder model. And then the end goal is to get to something like this, where we've got our digital display. So this would be really helpful for somebody in industry if you wanted to remotely monitor what was happening with your Raspberry Pi, where you've got our live understanding of what the temperature is at the CPU and the temperature at the sensor. And all of that relevant information coming in. And what we did is we turned it to a high power setting. So you can see the CPU load here is coming in from the Raspberry Pi into ThingWorks and shown on the mashup. CPU load increases, the temperatures increase, and the real temperature is increasing, and the digital twin temperature is increasing at about exactly the same amount, So ultimately, we're using Fluent to develop a reduced order model to tell us more about our physical component than we could otherwise. And so the reason that's really a powerful concept is because if you think about our fluent model, we don't just understand the temperature here and here. We understand the temperature at every point in the domain. We understand the pressure and the velocity at every point in the domain as a function of time. So not only do we have information about the sensors, from the sensors about the system, but we can also have information from the reduced order model about any point in this domain. Okay, and we've built a digital twin that allows us to remotely monitor and keep all of that data. And yeah, there's a bunch of different uses. If you're interested in digital twins, check out that site, simulation enabled digital twin from Leap, and yeah, I recommend it. So does anybody have any questions on this model specifically before we move on? Nope, all good. Okay, so that's our heat transfer section. All right, well, let's have a little look at some multi-phase then. We'll just go through a tutorial model. And maybe we'll have another look at this car model again from yesterday as well. So this is a tutorial model. You can get this from the learn.leapost website. And here, tank flush workshop. This one is a lot more in depth. It is an older version as well, this floating bodies one. But if you are interested in VOF and you are interested in some more high fidelity applications, a bit more complex applications, then go through this one. But because it is the instructions are in for an older version, I would recommend going through a bunch of different tutorials in the newer version so you get a good understanding of how to use the software before you go getting instructions for an older version, because it won't necessarily be able to tell you exactly what to click or where to click it. You just have to have an understanding of what they're doing in that one so you can do it in the newer version. Can you show us how to set Fluent always save the case data under .h5 format? A .cas format won't retain overset mesh connectivity. That's true. It also, I think, doesn't save as much information about DPM. It also is faster to read and write. In the new versions, 2020 R2 and 2021 R1, the .h5 format is default, and I'm not sure if you can save in .h5 in earlier versions. So if you have to use an earlier version, maybe shoot support an email and just see if that's the case. But this will automatically write the case out as .h5 just because it's the default to do that now. You can change it back to .case, and that can be helpful because some applications still want to read in .case rather than .h5, and that's in here. So if you go to File, Preferences, change from CFF to Legacy, it'll change it back to being saving in .case without the .h5. So yeah, I'm not sure if the older models can save in .h5 though. Okay, so in this case, the application is a flushing tank. So we want to basically have some fluid in there. So I'll send these questions. Could you show us how to generate graphs based on the results? We went through that yesterday. There might be some graphs that will generate automatically here. If we get to it, I will. But otherwise, it's in the content yesterday. Where are the recordings? I'll let you know, Roberto, when they're going to be, where they're going to be. That you'll get an email, but they should be up on YouTube within a day or two. Alrighty. So in this workshop, use the VOF model to simulate the filling and emptying of a water tank. Okay, so you can see here that we're just going to have some flow coming in of water, but you can see there's two phases. So the important part here is there's two phases. So we're introducing more complexity into our CFD model. So you can see we've got a mesh. This is 2D instead of 3D. So when we're doing our fluent, just remember to click 2D up here instead of 3D. It used to be that if you didn't select the right dimension, the error message would not be necessarily that helpful in telling you that you're in the wrong dimensions. But luckily now it does tell you if you're in 3D, you try to import a 2D case, it says wrong dimensions. It never used to do that. So people would always get confused as to why it wouldn't import their case file. Okay, so now we've got our mesh in. Our mesh is only 12,000, 13,000 cells, so 2D case. It's nice and quick, going to be nice, quick to solve. Our quality of the mesh is going to be really high. Oh, it's not as high as I expected, 0.99. It's not too bad. You can see it's a nice structured grid. And really the important thing here is we need to turn on multi-phase and volume of fluids. So in our models, we're turning on volume of fluids, multi-phase, and that allows us to have multiple different phases, fluids and gases. Our volume fraction parameters formulation is explicit, and we want a nice sharp interface. Certain applications don't always require a sharp interface, but in this case, we will apply the sharp interface. A lot of this stuff, I'm going to be very broad strokes with it. I haven't done that much multi-phase modeling myself, and so a lot more of the information will be in the tutorial itself and in the help files. But we're going to go through this very, very quickly, very broadly. So once we have our volume of fluids turned on, we can then specify the different phases, so our primary phase and our secondary phase. So once we need to bring in some material from the database or create our own in order to specify that as a second phase. In this case, we've already got water liquid specified. So we got phase material water, primary phase, air is the secondary phase. And we've set up a phase interaction between the two, so our surface tension coefficient. It's not always necessary to have a surface tension, but in this case it is. How many phases can be used in a VOF model? I believe it's just two, because you've got fluids and gases. If you've got multiple types of gases, it's a species model. And if you've got multiple types of fluids, it's a species model as well. So having fluids and gases is multi-phase, but there's only two. But you can have multiple different materials within that. But you'd have to then turn on, if you've got two different types of fluids, fluids, or two different types of gases, you'll then need to go into species. Okay, which we're not going to cover today. In this case, it's using K omega SST as the defaults. And we've got our one cell zone and then our boundaries. So in this case, they're using a pressure inlet boundary condition at zero pressure. Works much in the same way as a pressure outlet. It's no effect on the flow, just allows things to come through. And we've got our pressure outlets here. So we need to make sure that when we're doing volume of fluids or multi-phase, that our backflow specification is specified properly. So we change our phase to being air. And then when we open up our pressure outlet again, we get a different look at the pressure outlet settings, and where backflow volume fraction of air should be 1, because we don't want any water coming through in here. Because any backflow, which there would be, because air is, going to be moving in and out. If the fluid in the domain is moving in and out, we don't want air just falling through there. That would be unphysical. Same thing with this outlet. Backflow volume fraction of air is 1. The walls are just zero slip walls. Just looking through the tutorial, see if there's anything I missed. So we want water at the inlet to be coming in at 20 kilograms per second. So water's coming in here at 20 kilograms per second. So remember, we need to change our phase to water before we can specify how much is coming in. Or maybe not, maybe we do that in a mixture. So we've changed it to a mass flow inlet. So a mass flow inlet, we're obviously going to have our conditions specified as kilograms per second. In this case, it's 20 kilograms per second. Specifying backflow. And we need to initialize with some value of some amount of water in the tank. So let's initialize to start with just standard. So that's going to clear all the solution data that was in there and put, when we use a standard initialization, we're not iterating, we're just applying each of these values to every single cell. So every single cell has a gauge pressure of 0, an X Y velocity of 0, and air volume fraction of 1. So if we were to do VOF contour, we'd see that it's all filled with air. Volume fraction of water is 0. But we need to patch. So there should be a cell register. There is. You can see that we can create a cell register based on X and Y coordinates, or X, Y, Z coordinates for a 3D case. And this is just cutting out all the cells in this dimensional domain. And the reason we want to do that is because we want to patch, much like we were patching with the solution variables before, when we wanted to apply the solved solution from another case onto a new mesh, we're patching it in here. But we're only using this register, not the whole domain. And we're using our volume fraction of air to be 0. Does that work? No. Let's try that. Okay, that worked. So we needed to go patch, make sure we're looking at air, volume fraction, value of 0 into this region, and we patch that in. And now we're starting with a some level of fluid, level of water already in here. One thing that we're doing in here is we're specifying some autosave function. So that's another thing that we can do, especially when we're doing, you'd like to do when we're doing transient cases. So we want to autosave every X time steps. We might not want to autosave every time step. It might not be a problem with a case like this because it's not a very big mesh, so we don't have a lot of solution data to retain. But we want to save data every X amount of time steps, depending on how many time steps we have to solve for. Define a command to modify the boundary condition after 0.25 seconds. So we want that tank flush to run for 0.25 seconds. So this is another auto activity. It's already been specified. So remember when we were going through the 2E in here, and we can type certain things and that'll do certain commands. So if I was to say solve initialize, hyb initialize, that'll run a hybrid initialization. So these commands can be copy and pasted in. You can have multiple lines of commands and it'll run through them. And so that's the basis for a journal file. These commands can also be used in this execute commands function. So we can see that every 100 iterations, it's going to run command 1. Every 100 time steps, sorry. And that's going to say define boundary condition, the inlet as a pressure inlet. Okay, so if I was to run that command, and then I check my inlet, it's now a pressure inlet. Let's make that, let's change it back. Check that we've got water flow. Respecify that. And so obviously what this is saying is after 100 iterations, after 100 time steps, sorry, turn the flow off. Okay, in command 2, define boundary conditions, pressure inlet, air number 1. So at the same time, it's basically specifying the pressure inlet to have air coming in if it needs to. So our backflow quantity, our backflow phase will be air. Okay, let's just see if we've got our animation. So when we're running transient, it's often really helpful to have animations, and animations then will save out images rather than having to have the whole case and data file saved for each time step. And that's in here as well. Solution animations have already been created. So it's called whatever name, recording every time step. If we're going through a lot of time steps, you can have that every 10 time steps. And you use a contour that's already been created. So essentially, it's going to take that picture every time step. All right, let's just run through a bunch of time steps and watch it solve. I'll just pause it for the moment. So one of the major differences between transient and steady state is when we're solving transient, we actually don't want to have any more than 20 iterations per time step. And to be honest, we don't really want to have any more than 3 or 4 iterations per time step. So for a really well-defined model, something that has good convergence behavior, we're expecting about 2 or 3 iterations per time step. Remember, in a steady state case, we might have to solve for 1,000 or 2,000 iterations to get a converged solution. When we're doing transient case, one of the parts of transient cases is that it doesn't require as many per time step and many iterations per time step, but obviously you're solving for a lot of time steps generally because you need quite small numbers in order to get good convergence behavior. So you can see that this might start to drop, hopefully, these iterations. So in my mind, oh, there we go. If I was to be setting this model up, I might like to see a behavior that looks more like this, where it's just dropping rather than, and what we can do, stop at the end of the time step. Obviously, that's because there's quite a lot going on in here. But I might like to reduce that time step size by some factor, just to see if I can get a little bit better convergence like that. That's what you want to see. Few iterations per time step, and it runs through, you'll actually save time. So that's half the time step size, less than half, but it'll do more iterations in this, more time steps in the same time, because we're getting better behavior, better convergence behavior. And you can see this is obviously set up to only record every few time steps. So this updates every few time steps. Alrighty. So when we do animations, they come out with a couple of different file types. You'll get a .cxa file and then some .hsf files, and you can find those if you're using Workbench. You can find those in the file structure. So wherever this is saved, oh, this is the wrong one. Where is the, so this will be being saved in Fluent Multiphase Fluent in my directory. Here we go. So this is the directory, so it's automatically saved them out into here. This is the name of the animation. We've got a .cxa file, and that's just a pointer file. So it points to all of these .hsf, and they're obviously our frames. So if we wanted to open this animation, we can open that with another Fluent window, but we can use the current Fluent window, and it'll already be loaded and ready to go. So we can go from solution animations, that's where we created it, down to animations here and playback. You can see it's already loaded in. Well, that's some funky behavior. It looks like maybe we've got flow, it's flowing upwards. Negative G. What is going on there? Let's turn that to positive, see what happens. We'll start from the same point. We won't start again. Let's see if we can get that flow coming back down. Might have made it worse by the look of it. Let's find the videos from the training material so we don't have to spend too much time on this. That's what it should look like. A bit of flow in, and it then flushes away. Looks like we either had too much mass flow speed, or the specification of gravity was in the wrong direction. Yeah, I think maybe the value for velocity at the inlet might have been a bit high. Value for mass flow at the inlet might have been a bit high. But it did seem like gravity was struggling to have much of an effect. Let's try a run again with a lower gravity. Operating conditions, gravity, let's go 9.81. Negative, so we know what that's exactly what's specified. Okay. We're gonna reinitialize. Then we're gonna patch that fluid in. Double check that's what we've done. There we go. And let's set it to solve in the background, see what happens. Oh, hang on. Stop at the end of the time step. We need to turn on the water flow. I have to assume gravity is working correctly because none of this fluid is disturbed. There's fluid coming in. Let's just leave that to solve for the moment. Okay, so that's multi-phase. Does anyone have any questions on that before we move forward? Now, a few of you were crying out to do multi-phase yesterday, so remember that there is all of this training material in here, and this really cool model where we've got a floating object. Okay. More about mass flow inlet. What exactly would you like to know, Ashi? Turbulence models for multi-phase flows. That's a difficult question to answer. Once again, it's case specific. Well, we're not really getting great convergence behavior here. Let's try and get this running more smoothly. Yeah, once again, a very case-specific problem. K omega SST is still really applicable for most applications in multi-phase. But depending on the application, if you have high turbulence, you need to understand that turbulence. You need to be going into LES models and things like that. Is there a way to confine the two phases with a non-slip surface? You can have separate cell zones, so multiple different cell zone areas, and different fluids in each. Yes. In terms of the mass flow inlet, yeah. There's a bunch of different inlets that we can have. So we can have velocity inlet, pressure inlet, and mass flow inlet. There's also pressure far field, which can be useful for big 3D applications. And that's useful for more hypersonics, but there's not really much to a mass flow inlet. It's very similar to your pressure inlet or your velocity inlet, where you specify exactly how much is coming in, which in this case you have to specify through the mixture, through the phase. But then the other thing is the turbulence specification. So very similar. So it's just gonna calculate how much fluid or gas is coming into the domain, and then what the turbulent quantities of that fluid are. How is the viscosity different between the two phases modeled in Fluent? Well, the viscosity is specified in here. So the viscosity of air, it's obviously going to be a lot lower than the viscosity of water, but each of those fluids has its own viscosity. So that'll be factored into your Reynolds average Navier-Stokes equations in your mass continuity, I believe, in your pressure continuity Reynolds average Navier-Stokes equation. There we go. Gravity seems to be working. We're just going to have one massive fluid because it was coming in at a slower rate. Just blob in, and maybe some will splash over the edge. A little bit different boundary conditions to the actual tutorial, but still solving a model with just separate different boundary conditions. Okay, we'll leave that to solve in the background. Maybe get a animation out of it for later. Okay, so there's a couple more models I want to take you through, some more complicated models just out of interest. First one we're going to look at is an adjoint model. Actually, you can get a case file of this model. It's on the learn.lepos website right here. So you just download multi-phase modules, you get all of them. And that should have a solved model in there and everything that you need. Alrighty, let's open up a new adjoint model, and I'll tell you about what that is. An adjoint is a it's an optimization model. It's a really interesting way of optimizing aerodynamic shapes. Yeah, that model definitely does have a problem with convergence. For just the tutorial at the moment, I think we'll probably just leave it for today. Won't go too much into it. We're getting into a little bit more support style stuff, how we're going to run through and fix this model up. But There is, because you can see also another way we would know that there's a problem with convergence is it going through all 20 iterations per time step. So if I was to stop at the end of the time step, you can see that each time step, so 246 more time steps to go. So each time step's going from 20 iterations down to 0, and then into the next iteration, into the next time step, 20 down to 0, into the next time step. Yeah, so there's definitely some work that needs to be done to improve the convergence behavior of that model. Let's just leave it to calculate anyway and see what happens. All right, that's what happens when you do things live. All righty, file, read in. I hope we're in 3D. Could you explain the difference between time step convergence criteria, and solution convergence? And if I'm using the time step convergence, how could I make sure that the solution is converged? Well, so they're both very similar, so that there's not really any difference. They're both using residuals to assess convergence, but you're either solving steady state or you're solving transient. So in a transient case, you're converging every time step, and you should be converging within 20 iterations. In the steady state case, you can use as many iterations as necessary to get to a solution. So, there's plenty of solutions that can take upwards of 5,000 iterations to get to a fully converged solution. Okay, so the adjoint. Let me see if I can quickly get up some slides for that. You can see here that's it'll be in the notes that you get. You can also get some adjoint tutorials from the learn.lepos site as well. Okay, so the whole purpose of adjoint is to get a optimized aerodynamic shape. Okay, now what the adjoint is a mathematical trick where you solve for the derivatives or sensitivities of a output observable quantity of interest at each cell location in the domain. So you solve for a flow solution, and then once you've solved for a flow solution, so your flow solution is your standard, solution, and then we can go into our observables and our adjoint solution. We solve our adjoint, and that gives us our sensitivities of so derivatives of the observable at each location. So that would be something like, okay, I want to know how to maximize for lift. It'll look at the lift production at each location on the surface and the sensitivity of that lift production to a changing shape, and then you'll change the shape a little bit, and then you'll go back and solve the flow solution. So we don't do this in one go. It happens in many, many iterations, but you can see that this original profile is just say a NACA 12, wanting to optimize for lift over drag. You run through a bunch of iterations, and you can see that you get this optimized shape. So it's a really cool technique that is available in Fluent. And what we did is we did this for a client who wanted to use adjoint to optimize for thrust over torque for a propeller. So he gave us a representative propeller shape, something which is just a NACA, and we put it into this domain. So you can see it's quite an odd shaped domain, and the reason that we had to do that is because we basically needed to reduce the amount of reversed flow at the boundaries. Because one of the things with an adjoint solution, remember we solve our flow solution, so we're solving our flow solution, and then we solve our adjoint solution. The adjoint solution stability is highly contingent on the convergent stability of the flow solution. So if we're not getting our residuals dropping in a nice stable way, we're not going to get a good adjoint solution. Remember, the adjoint solution is where we solve our sensitivities. So basically changing the shape to be this like an egg shape, this whole outlet here has less reverse flow, because obviously the flow is coming down from the inlet, and then the propeller is spinning and forcing that flow down further. So changing the shape reduced the amount of backflow and allowed us to get a more stable solution. And that's why that looks like it does. Now, in this case, we've got a moving reference frame, which I haven't spoken about yet. But a moving reference frame is a mathematical technique that allows us to say that this is spinning in space, but solve for a steady state solution. So we can see here, we look at the cell zone. So in this case, we turn on frame motion and we say this whole cell zone is spinning in space. So about the negative y-axis, we're rotating at 500 radians per second. Adjoint solver, as I understand it, Zakaria, is a fluent application only. For a simulation, should the lowest points of the sawtooth also converge? I'm not 100% sure what that means, Angus. It'll always start at some higher value of residual and work its way down. Sorry, we're jumping back into some questions here. Yeah, so moving reference frame. Here we've got our rotational velocity. So we're specifying that the whole domain is rotating. But the actual boundaries being an outlet and this being a periodic boundary won't have any effect on the flow. The only thing that will actually be rotating in terms of, its effect on the flow will be this propeller here. And the other thing that's cool about this one is that we have a periodic boundary condition. So that's split in half, and you have to have a same mesh or a mirrored mesh on either side of the center plane. And that just says that the flow coming into this side will be going out of this side. So flow coming out of here will be coming into that side. And that allows us to do cyclic symmetry for this model. So we know that we have a symmetric body or cyclic symmetric about the Y rotation axis. So we implement a periodic plane to reduce mesh on mesh elements. So we solve our flow solution, we specify our observables. Our observable is ratio 1, which is our force, which is our thrust force over our moment force. So you can see our force O1, which is our thrust force over our moment force. And then we leave all these methods as default and we calculate for our adjoint solution. And once we get that, we can then go into our design tool. And modify our mesh, okay? Once we modify our mesh, it's going to move it according to what it thinks is the best way to optimize for that given variable of interest, so that given observable. And we'll do that many different times over. So we modify the mesh, it'll remesh, it'll move the mesh a little bit, just a really tiny bit, and then we go back and solve the flow solution. Okay, so we do that many times over. Let me see, I'll just bring up the slide, the pictures of the optimized solution. A little bit hard to see on that one. There we go. You can kind of see that this is a mid plane taken through a cross section taken through the mid of the wing. You can see that the shape is updated. Taking an oil flow. So it's a really cool way of kind of getting an optimized shape. This increased the thrust by over 30% and increased the lift over drag by over 15%. Okay, so and that was without getting to the absolute maximum that we could have for those simulations. So you can see here, this is the start point. So we've got our oil flow, which is just another type of post-processing that we can do in Fluent. You can see there's a lot of that flow escaping over into the vortice, into the trailing tip vortice. In this case, where the shape has been optimized, it's kind of stretched that the trailing edge out and made this a little bit higher. So it's almost acting like an end plate. You can see the oil flow goes to go off and then is straightened. So keeping that flow on there for longer is obviously increasing the amount of lift that wing is producing. So that's adjoint solution. You can see here there's a bunch of tutorials you can go through where they optimize for the shape of a pipe for a reduction in pressure drop, optimize the shape of the airfoil for lift over drag, and you can see that there's quite a few actually. So worth having a look if you're interested in the adjoint solver. For DPM, could you please explain how to export the particles tracked from Fluent to CFD post? That is more of a support question. So if you want to email that one to support, they'll be able to help you on there. Is the iterative optimization process automatic or manual? It can be automatic and it can be manual. So in this case, if you use the gradient-based optimizer, it actually does it automatically. So you can specify what your target goal is, a bunch of these settings in here, and you can set it to run for a bunch of iterations and it'll do it all automatically. I like to do it manually until I know that the solution is robust, because like I said, getting your adjoint iterations to converge can be a little bit difficult, and running a automated method and walking away can often lead to you just coming back and going, oh, it only did a few iterations and then crashed. Is it easy to extract the resulting surface? Yes, it is. It's in here. You can just export the STL. Angus, I mean, for a transient simulation, for which residuals converge within time steps, should the lowest residual for each subsequent decrease do? No, it shouldn't. Actually, they should remain fairly constant. So it should look like this, but only say 1 or 2 iterations per time step, and we want that time step to be going below 1e to the -3. So as long as the bottom one goes to 1e to the -3, then it's all converged. And then, yeah, so it should stay a constant line along. All righty, let's try and figure out what happened here. A quick look at the animation. Wow, it's almost like the gravity is so high that it's shot it out and splashed it. Meters per second squared. Meters per second squared. That's really interesting. I wonder why that behavior. It's like once it gets to a certain point, it just rockets down. So it seems to me that the problem is either in gravity or, I mean, the inlet condition doesn't look too bad because it kind of comes in at a, and then just shoots. That'll be something worth looking into. Alrighty. If I have a moving wall in the questions, does Fluent capture the change of my moment center? In the case that we just went through, Huey, it was a steady state case, so there is no change to the moment center. If you're running something with like a 6DOF solver, then the whole body will move. There will be an update to your moment center and to your reference monitor point specifications. Yeah, sorry, Raman, that is in design tab. So when we use, we'll go back to our adjoint. You can see that design tool, export STL, and you pick out the surfaces that you want to export. And it'll come out as an STL. Then you can do what you want with that with your geometry editing tools. Reversed flow on an outlet boundary. So if you think about it, we'll put the outlet here. There's flow coming down, but there's also going to be a wake region around this propeller. So the flow may not, it's not necessarily going to be some laminar downward motion of flow. There will be some chaotic nature to it, and that will mean that there'll be places where the flow will be wanting to come in, go out, and places where the flow will wanting to be come in. So that's what your outflow is. And so it's important, especially when you have things like a thermal condition, you want to make sure that the flow coming back in has a relevant temperature, because it's not recording, once the flow's out of the domain, it's not recording what's right there in terms of flow. Otherwise, that would be more flow domain. So flow coming in has to have some assumption for its temperature, has to have some assumption for its phase. So especially in multi-phase, really important that your backflow has a relevant phase to it. We don't want water just pouring in through outlet boundaries. Hopefully that answers your question, Ezra. Okay, I've got one more case that I'd like to show you. And this one's called overset, because I think overset's a really interesting application for Fluent as well. Okay, so this is what we call an overset grid. An overset grid is really helpful because what you can do is you can embed a cell zone into a larger cell zone. So what we call a component mesh into a larger background grid, and they'll overlap. But what you can do is you can interpolate the solution between the background grid and the component grid. And I'll show you what that means when everything loads. Okay, so you can see we've got a wing. It looks like kind of some type of jet wing. It's got a pylon and then a stall. And so we want to the whole point of this case is a validation case that's done, that's been done for many years in CFD to try and validate for either a dynamic mesh method or an overset method. And what the purpose is to have a store separating from the wing and to understand that the aerodynamic performance of the wing through that process isn't compromised. Okay, so that was the initial application, but now it's used as a bit of a validation case. You can see here, like I said, we've got our background cell zone, so a big cell zone that covers all of the area, and then this component mesh, which just houses the store. Okay, and now the whole thing is you have your flow coming in at some velocity, so it comes through all of these elements. For those of you who are interested, yesterday we were talking about having a buffer layer between our polyhex core. That's what that looks like. So to avoid the 1 to 8 octree transition, we've got our some size of hex core, our polyhedral buffer layer, and then more hex core. So to avoid that transition, that's what that is there. But so we've got our flow coming in these cells, in these cells, in these cells, will get interpolated into these cells, and then it's in the component grid. And then once it's on its way back out, it's getting reinterpolated back into the background grid. And the reason we want to do that is because it allows us to avoid things like dynamic mesh. So we don't have to remesh our domain. So if you don't do this with overset, because we want this store to be dropping and moving. If we don't do it with overset, we have everything in the same grid. As the store drops away, we have to remesh the domain constantly at each time step. And that can cause problems with, well, it doesn't cause problems. It's just a different way of doing things. But there's different difficulties involved with having an overset grid and having a dynamic mesh grid. In a dynamic mesh grid, you need to make sure your remeshing settings are the same, are such that you're getting the same definition of grid every time it remeshes, and that that your diffusion methods or whatever methods you're using are working correctly, your parameters are specified correctly. In the overset method, you need to make sure that every time the object of interest, the component mesh moves, you're still able to generate a high quality interpolation interface. Okay, so you need to have a certain amount of cells in between to allow it to interpolate fully, and you're not going to have what's called orphan cells. And as long as that's the case, then the whole thing can move in space without having to remesh. But the other thing is that a overset mesh method is non-conservative, okay? Because it has to interpolate between background and component grid, it's non-conservative in that you lose that conservation of mass. So that can affect the accuracy, but generally doesn't affect it drastically. So no dynamic meshing required, greater control over mesh refinement and quality, less troubleshooting and guessing, and no orphan cells. 5 days of runtime for a 16-core machine for this specific case. And you can see what we're showing there on that GIF is the interface between the background grid and the component grid. So the blue cells are solver cells, the red cells are donor cells. So we're donating solution information into the component grid, and then the component grid is receiving it, and then the reverse is happening at the back end. Okay, I'll show you what that looks like in here. If I can. There we go. So this is a transonic case. So the Mach numbers, I think, is 0.9 for this case. So there is some kind of shock effects, things like that. I'm just trying to get a good view of the domain itself. Okay, there we go. There's our domain. So our wing, our pylon, our store, and then our domain. And so in this case, let's have a look through our mesh. So this case has over 9 million cells total. .012. So not a great orthogonal quality, but what that goes to show is that orthogonal quality isn't the be all and end all. You can have solutions with lower minimal orthogonal qualities than 0.1. But the reason we want to get to 0.1 as a best practice, or even 0.15, is because at that point you can remove any potential that your solution divergence or your solution instability is due to a poor mesh quality. Okay, so sometimes you still can get a decent convergence stability with a lower mesh quality, but we want to remove the possibility that that's even the case by having a 0.15 high enough mesh quality to say that. Okay, so once again, everything we talk about in CFD is very case specific. There are not often golden rules that apply to everything, but yeah, so that's the point with minimal orthogonal quality. Okay, so in this case, we can got our two boundary conditions, two cell zones, sorry. So our two separate cell zones. So there's something with the display here. That's better. So we've got our two cell zones. That's our component mesh. So inside that has the store and our background mesh. And the way that we specify that is we set up this overset boundary condition on the external surface of this. And then we can come into here and go overset, call OVS between the background and the component zone, and it'll use that overset boundary condition to specify where the overset interface is going to be. Now you would have noticed already that we have some solution data already in here because we've solved our steady state case. Question, is the enclosure is any type or only oval shape? For this specific case, we've just gone with an oval shape, or it's not really an oval shape, it's a hemisphere kind of cylinder. But you can have an enclosure any shape that you want, as long as it's far enough, the boundaries are far enough away from the region of interest, so that they're not having an effect on the solution. So we can see, well, let's go through the boundary conditions quickly while we're here. Pressure far field is a new type of boundary that we haven't seen yet, and that is, I'll show you what it's all of that. It's all of the external walls, and what you can do there is you just specify the direction of the flow. And so component flow direction, it's in positive X at Mach number 0.95. And this is really good for any time you have transonic or supersonic flow conditions. A pressure far field is mathematically the best option. So we don't necessarily even need an outlet condition because all of this just has the flow going in that direction. That's how a pressure far field is specified. This obviously is our is a symmetry plane, the center here. Everything else is zero slip wall. Another thing that we have to have turned on is we need to have the mass of the object. And that is specified in our user-defined function. I believe the dynamic mesh hasn't been turned on in this case. But in order to get it moving in space is we'd have our gravity turned on, which it is. And then we'd have our mesh dynamic mesh turned on, because we need to have our weight and our moments of inertia specified for our store, so we can have it falling away with the right velocity, and it's also being affected by the pressure forces in the right way in terms of its rotations and translations. Huey, can you show us how to set up the dynamic mesh? And do I need to tell Fluent that the wall is moving in wall boundary condition setup? So you do need to turn on dynamic mesh. In this case, we create edit in here, and we say that it's a rigid body. And so the store is a rigid body with some center of gravity location and some orientation. And then we can create that here, but we need to have a UDF specified. So remember yesterday we went through UDF thing, the UDF applications. This is a really good case that needs a UDF. So UDF is our C program. It's a snippet of code set up in C. And this is specified that the mass of the object is this many kilograms, that the rotational inertias about each axis is this amount, and there's also ejector forces on the front and the back of the pylon to force the object away. And this just says that if this the front of the object is less than this distance away from the pylon, then apply this force and moment, and same with the rear. So once it's far enough away from the pylon, these forces stop being effective. So once that's specified in here with our UDF profile, then that object has those mass parameters and moment parameters, the rotational inertia parameters that allow it to move in space in a realistic way. Okay, so you can see that we did have some solution data brought in already. So we solved our steady state case first. You can see here that we've got static pressure. You can see there's some shocks. I can show you a Schlieren gradient. Hopefully one of these ones. It's our Mach numbers. Raman, if you're interested in the mathematics of the symmetry profile, the symmetry boundary condition, I would recommend you go into the help files and have a look through there. Just have a little search of symmetry, the symmetry plane in the theory guide. That's modeling radiation, so we're not interested in that one. So Ansys Fluent assumes zero flux of all quantities across a symmetry boundary. There is no convective flux across a symmetry plane. So any gradients, your shear gradient, shear force gradient will be zero. Your pressure gradient will be zero, and there's no flux of any quantity across a symmetry boundary. Also, zero normal velocity and zero normal gradients. So if you want to know specifics about those kinds of things, then yeah, get used to using the help files because it's really helpful amount of information in there. Yeah, you're right. The symmetry plane is not 100% applicable for this case, as there is a unless there's another wing on the other side with exactly the same thing going on, not a fuselage body. But it's just the way that's been specified for the validation cases. So all the validation cases are done with the same boundary conditions, and that symmetry plane is used for all. And that's just to cut down on the computational expense. Okay, so well, this is the the steady state solution. So this is your initial static pressure plot. So because of these forces, this store is going to start falling away. So this and the force of gravity, the store is going to start falling away. And as you've seen in the slides before, that it does so in time. You can see here that we've matched up with using the overset method rather than dynamic mesh. You can see we've matched up the longitudinal, lateral, and vertical translations. And this is what it looked like as it was going through. So on the right, you can see we've got a Schlieren. A Schlieren is basically density gradients. It's an advanced post-processing technique because you have to turn on expert parameters to get density gradients in each direction, and then get the sum of all those, or the square root of the sum of the squares of all the density gradients in each direction, and that'll give you what is effectively the Schlieren image. Okay, well, those are all the models I wanted to show you today. Hopefully we could see, you got to see some cool things that CFD can do. Did you have any questions on any of those? Or on any of the other content that we've covered in the last 4 days? Otherwise, I think we can all have an early mark for the day. This video will be posted in YouTube, Sebastian, yes. Remember, there's the Leap Learning Hub in here, learn.leapos.com.au. Make sure you go through that. Also, make sure that that you write these down. So if you have any questions about anything we've covered, or about digital twins we went through very briefly, make sure you shoot me an email. I may direct you to support depending on what the question is. That's our support line that we use to help out people with specific questions. We do have coupled one-way and coupled FSI, be in the fluids, I believe. So you can see here in fluid multiphysics, there are some two-way FSI for a hyperelastic flap, one-way FSI where you map the pressures onto a structural component and see what the deflection is. a two-way thermal FSI. Make sure you go onto there and have a look through there if you're interested in those applications. Oh, Ezra, the parallel meshing is very easy to do. Oops. In the launcher window, just specify meshing and specify how many processes meshing. Tutorials on shape optimization, Akash, yes. In here again. Adjoint solver. So all of these are tutorials. Just download adjoint modules and you can go through any of these. The email addresses are in the chat. So if you have any questions at a later date, make sure to shoot us an email. Okay, guys, if there's no more questions, thanks for coming. Thanks for attending. Appreciate you all taking the time. Hopefully you found it informative. And I hope to hear from you soon as well, for any of you that do carry on with this kind of work. Alrighty, thanks very much. I'll catch you guys later.